Hi, good morning, everyone. Right, guys, give me a minute. Did you get YouTube? Oh, no. Fine. What is the tutor you have got? Nuclear, right? Anyway, we have questions from the previous tutor, right? Yeah, we did, right? Hold on, give me a minute. Guys, what are the questions for homework? Starting from what? Starting from 15th. Fifteenth was a homework, is it? 15th. Let's turn to question 15. Right. Question 15. In 1931, Sloan and Lawrence built a linear accelerator with several drift tubes. They used the LINAC to accelerate mercury ions up to energies of 1.26 mega electron volts.
So we can't see the screen, sir.
Okay, the behavior of the particles was non-relativistic. Still, we haven't done about particle accelerators, but this question can be done even without that. Right? The kinetic energy of an unrelativistic particle of mass m with momentum p is given by the equation E equals p square over 2m. Derive this formula. So guys, this is the relationship between the kinetic energy and the momentum. So kinetic energy is given by Ek equals half mv square. And if you use P equals mv, V equals P over m. Okay, if I use that here, half into m into v square, v can be replaced with p over m square. That is half m. P over m square is p square over m square. So one of these m's will cancel off and you are left with p square over 2m. That will be the kinetic energy of a particle with mass m who has a momentum p. Okay. Right. Right. There's the next one. A mercury ion with kinetic energy given leaves a drift tube as shown. Calculate the momentum of the mercury ion when it reaches the next drift tube. Calculate the momentum of the mercury ion when it reaches the next drift tube. Mass of the mercury ion is given. And charge of the mercury ion is given. Electric field strength between the drift tubes is given. And the distance between the tubes is given. Okay. One way that I can do this is I can use it electric field strength equals V over D, potential difference between these two divided by the distance. So V equals E into D. So we know the electric field strength, which is 7.64 into 10 to the power 6. The distance between them is 5.50 into 10 to the power minus 3. This will give you the potential difference between the two drift tubes. 7.64, 5.5, which is 42,000. 20 volts is a potential difference. So the gain in kinetic energy or the work done will be E equals VQ, which is potential difference, which is 42,020, multiplied by the charge of the particle is 1.6 into 10 to the power minus 19 coulombs. So 42,020 to 1.6 into 10 to the power minus 19. 6.7232 into 10 to the power minus 15 joules. This is the work done on the particle, or this will be the additional kinetic energy the particle will be gaining. Okay. Already the particle had a kinetic energy of how much? 6.42 into 10 to the power minus 15 joules when it is leaving the first drift tube. So when it is reaching the other side, its new total kinetic energy, if I take it to be EK, that will be the initial one, which is 6.42, plus now the one is 6.72 into 10 to the power minus 15. Already you had 6.42. Now in addition, you are getting another 6.72 into 10 to the power minus 15 will be 1.314 into 10 to the power minus 14 joules will be the kinetic energy of the particle when it reaches the other tube. Now from the previous part, we know the relationship between momentum and kinetic energy. So we are told to find the momentum of the particle when it reaches the other tube. So guys, P square equals 2 MEK. Correct? So P will be the square root of this. So 2 into the mass of the particle is given 3.32 into 10 to the power minus 25 into kinetic energy is 1.314 into 10 to the power minus 14. That gives you the P square, and get the square root of that. I'm getting 9.34 into 10 to the power minus 20 Newton seconds. Okay, have done this. But this answer. Okay. Done. What's next? Question 20. 20 is not a homework. It was before. So I have done 20. We'll do 20. We haven't done it, right? Right. Let's question 20. The train on a model railway is powered by contact with the rail. Contact with the rail. The train sometimes loses contact with the rail. The diagram shows a circuit that can maintain power for an electronic controller on the train even when the power is disconnected for a short time. The switch represents the contact between the train and the rails. Okay. So what are they saying is, even when the switch is open, still there will be power supplied to the electronic controller for a short period. Okay. Explain how this circuit can maintain power to the electronic controller if the switch is open for a short time. So where is the electronic controller? Is somewhere here. So the energy is given to the controller by the battery. There's a 12-volt battery. So when the switch is closed, there is a current passing through the controller circuit and it will get the current and the power. So the question is how the circuit can maintain power to the electronic controller if the switch is open. When the switch is open,
It
there's
only
no
charges.
Yeah.
When it's closed, it charges the capacitor, right? But when it's open,
Yeah.
the capacitor can
So when it is
charge
charged, the
equally.
capacitor is charged. So when the switch is open, the capacitor will discharge its charge and there will be a current passing through the electronic controller. So the energy is supplied to the electronic controller. So you can write the capacitor is charged when the switch is closed. Full stop. Capacitor is charged when the switch is closed. Full stop. When the switch is open, when the switch is open, the capacitor will discharge and the current will pass through. The electronic controller. For a short period. Okay, right. Where the switch is open, the switch is open. Calculate the time taken for the potential difference across the capacitor to decrease to 4 volts. Assume that the resistance of the electronic controller is infinite. Okay. Capacitance of the capacitor is given 47 millifarads. Resistance of the resistor is given. There's a resistor here that is given 470 ohms. Okay. So initially, the moment the switch is open, the initial voltage of the capacitor will be 12 volts. So from 12 volts, it is reducing to 4 volts. We need to find what is the time taken. So simple. We can use the equation V equals V naught e to the power
So what
minus
do they mean by infinite
infinite resistance.
resistance?
There won't be a current passing through. It will have a voltage. Okay. Infinite resistance means, now imagine there is an infinite resistor here. So whatever the current which is coming from the capacitor will pass through this one. Since this has infinite resistance, current passing through this will be 0. Okay.
Yes.
That is the meaning of infinite resistance. So V equals V naught e to the power minus T over RC. We are supposed to find the T. There's another form of this equation, right? What is that? ln V is equal to ln V naught minus T over RC. We can use that here. So guys, ln V has come down to 4. ln initial voltage is 12. Minus T is what we want. Over the R is 470. Into the C is 0.047. To convert millifarads to farads, divide by 1000. So from here, if we get the T subjected, it will be ln 12 minus ln 4 and cross multiply with 417 to 0.047. I'm getting 24.3 seconds. Have you got this answer? Yes. Right. There's another part. The switch is closed at time t equals 0 and then opened at t equals 20 seconds. Sketch a graph on the axis below to show how the current I through the resistor varies with time. Right. Switch is closed at t equals 0. From 0 to 20, the switch is closed means, guys, the current through the resistor during this time will be, it's connected to the battery and it's a constant voltage. So it will be a constant current. Am I right? Correct? Until t equals 20, the current will be constant because it's a constant voltage. So now from t equals 20 onwards, and it's a 4 marker. So I don't know whether they are expecting the values as well. To be on the safe side, I will calculate it. Guys, initially the resistance is 470 ohms and the voltage is 12, means I can find the current. If I use V equals IR, V is 12, I into the R is 470. So I can find the initial current, which will be 12 divided by 470. That is 0.0255 amperes. So if I get it in milliamperes, multiply by 1000, I'm getting 25.5 milliamperes. So since I notice here it's a 4 marker, I don't know whether marks are allocated for the figure values as well. Anyway, it's a matter of a few seconds to calculate the current. Just calculate it. That is the initial current. Okay. Then guys, current after that will decrease when the switch is open. The capacitor comes into play. So voltage through the capacitor will decrease with time. And for the voltage to reduce from 12 to 4 for the capacitor, we did the calculation in the previous part. It took a time of about 24.3 seconds. Correct? So in the next 20 seconds, listen to me carefully. In 24.3 seconds, the voltage has reduced from 12 to 4. Correct? So that is in 24.3 seconds. In the next 20 seconds, after 20 seconds, I believe the voltage is a bit more than 4. Am I right? Listen to me carefully. For the voltage of the capacitor to reduce from 12 to 4, it has taken 24.3 seconds as per the previous calculation. So we have to sketch the graph for up to 40 seconds. No, they have given, no, they haven't told up to 40 seconds. But then guys, the voltage will come to 4 volts when the time is 44.3 seconds. 44.3 seconds is, let me say here. Okay. When the time is 44.3 seconds, voltage will become 1/3. 12 becomes 4. So voltage becomes 1/3 means the current will also become 1/3. So here 25.5 means the 1/3 of it will be rough somewhere here. Okay. So I will take the current to be 1/3 of the initial value after 44.3 seconds. So it's going to be a graph like this. Yeah, ask me a question. Darling, 24.3 seconds from the moment the capacitor starts functioning. So here the capacitor starts functioning at 20 seconds. So from here, 24.3 seconds later means 44.3 is the time. When the time becomes 44.3, the voltage becomes 1/3. So the current becomes 1/3. Okay. So the shape has to be something like this. Which straight line? The first part. So for the first 20 seconds, the switch is closed. Capacitor is not in the business. Yeah, but we are talking about the voltage across this resistor. They're not talking about the electronic control. There is an electronic controller here. There are two gadomatics here. There is a fixed resistor here, which is 470 ohm. And there is an electronic controller here, which they haven't marked in the diagram. That's what they have put on 2 arrows and told to electronic controller. That goes to the electronic controller. That they haven't marked in the diagram. The question is, sketch a graph on the axis below to show how the current through the resistor varies. So we are speaking about how the current through this resistor varies. Not about the fixed resistor, maybe the electronic controller. Understood. If you have any questions, please ask. It's a 4 marker. It's like this. To be very honest, Unless otherwise, you don't see the marking scheme, you don't know for what the mark is allocated. Especially when it comes to this four marker, 5 marker, 6 marker. Even if I do the exam, I don't think I will be able to get the entire 6 marks for a 6 marker. So to be on the safe side, what I will do is, if I am a student, write everything that is relevant to that. So in this question, I don't know 4 marks is given for what. So shape is there, okay? But I don't think 4 marks will be given for that, just for the shape. So I did a calculation to just show, in case if they have allocated enough, we will get it, nothing to lose. Okay. This 44.3 seconds, I got it. From the previous part, we did a working and we got this 24.3 seconds now. That 24.3 seconds is the time taken for the voltage to come to 4 from 12. 12 to 4 means 1/3 of the initial value. So when the voltage becomes 1/3, current will also become 1/3 through the resistor. So initial current is 25.5 means, so that means I have a slight idea. For the current to become 1/3 of the original value, it will take 24.3 seconds from the moment you start using the capacitor. So you have started using the capacitor when the time is 20. So 20 plus 24.3 is 44.3. So that is the moment, that is the time at which the current through the resistor will become 1/3 of the initial value. Okay. Is that okay? Right, what's next? $22. At the Culham Center for Fusion Energy, CCFE, experiments are carried out on plasmas. A plasma is an ionized gas which is an electrical conductor. The plasma is contained in a donut-shaped vessel known as a tokamak. The current in the plasma is produced by steadily increasing a current. Current in the plasma is produced by steadily increasing a current in the coil passing through the hole at the center of it. It is given in the diagram. The plasma in the tokamak acts as a single conducting loop around the central coil. Okay. Explain how steadily increasing the current in the central coil produces a current in the plasma. So it's a 4 marker. So look at the points. When you increase the current in the coil, the magnetic field induced or magnetic field induced around it will increase. So when the magnetic field increases, the magnetic flux linkage will increase. Or you can say the magnetic field lines will cut the plasma. So there is a change in the magnetic flux linkage through the plasma. So there will be an EMF induced in the plasma. And since the plasma is a complete circuit, there will be a current passing in the circuit. The question is, explain how steadily increasing the current in the central coil produces a current in the plasma. Okay, I repeat, listen to me, listen, don't write. Increasing the current in the coil will increases the magnetic field induced. So the magnetic flux linkage through the plasma will increase. So there will be an EMF induced in the plasma. So since the plasma is a complete circuit, there will be a current in the plasma. Now answer my question for this. Now they are saying, explain how steadily increasing the current in the central coil produces a current in the plasma. Now what if I ask you, there is a current in the coil, but that current in the coil is not increasing, it's a constant current. Current in the coil is constant current. Okay. Will there be a current induced in plasma? No. Why not? The answer is the magnetic field is not changing. The magnetic flux linkage through the plasma, there will be a magnetic flux linkage through the plasma even in that case. But the magnetic flux linkage through the plasma will not be changing. According to Faraday's law, the EMF induced is proportional to the rate of change of magnetic flux linkage. So there have to be an EMF induced. The magnetic flux linkage should change. Understand? If the magnetic flux linkage is not changing, there won't be an EMF induced. Right, right, the answer. When there's a current in the coil, when there is a current in the coil, there will be a magnetic field induced around it, and it will cut the plasma. Full stop. When the current is increasing, when the current is increasing, come on, the magnetic flux linkage through the plasma will increase. So there will be an EMF induced in the plasma. So there will be an EMF induced in the plasma. Since the plasma is a closed circuit, there will be a current in the plasma. Since it is a closed circuit, there will be a current in the plasma. Okay. Right. Part B, the plasma can be considered to be a cylinder of length 13.2 meters and cross-sectional area 2.3 square meters. Show that the resistance of the plasma is about this much. This is from your AS levels. R equals rho L over A. Resistivity is given 3.3 into 10 to the power minus 8. The length is given 13.2. Cross-sectional area is given 2.3. I'm getting 1.89 into 10 to the power minus 7 ohms. Right. There's the next one. In a particular experiment, the current in the central coil is increased steadily. Current in the central coil is increased steadily from 0 to its maximum value in a time of 25 seconds. Current is increased from 0 to maximum in 25 seconds. When the current in the central coil reaches its maximum value, the magnetic flux linkage with the plasma is 16.9 meter. Okay. Calculate the heating power produced in the plasma. So guys, we can find the EMF induced in the plasma, which is change in magnetic flux linkage, 16.9 over the time taken, which is 25. EMF induced is equal to rate of change of magnetic flux linkage. Magnetic flux linkage increases from 0 to 16.9 in 25 seconds. So 16.9 divided by 25 will give you 0.676 volts. This is the EMF induced in the plasma. And in the previous part, we have calculated the resistance of the plasma. So to see the power produced in the plasma, we can use P equals V square over R. Do you remember this equation? Yes. What is the power in a electrical component? The power is given by what? P equals? Yeah. P equals VI. And then also V is equal to IR, right? Do you remember that? So if I take this I equals V over R and substitute it here, P equals V into V over R, right? V into V over R is V square over R. Check your AS levels. We have learned all three equations for power. P equals VI, P equals V square over R, P equals I square into R. There are three equations. Okay. Even if you don't remember, I believe at least you remember these two equations, P equals VI and V equals IR. From that, you can spontaneously derive that. P equals V square over R. Okay. So guys, now the V is 0.676. And that square over the R is 1.89 into 10 to the power minus 7. Which is 2.42 into 10 to the power 6 watts. Are you getting this answer? Here the E is the EMF induced. EMF induced is equal to rate of change of magnetic flux linkage. So E is the EMF, which is what I have taken here as the voltage. If you have any questions, you can ask me. What's next? 26. Right. There's a 26th one. A student is designing a night light for a child. When switched on, the night light should come on brightly and its intensity should then gradually decrease to 0. Nice. It's a good design, no? Did you do this question? Did you think about this design? You switch it on, when it will be on with maximum intensity, and gradually the intensity will go down. In 10 minutes, it comes to the time taken for the light intensity to decrease to 0 should be as close to 10 minutes as possible. So around 10 minutes, in around 10 minutes, the light will go off. So by the time you fall asleep, the light has gone off. Okay. That is the design. Look at this. The time taken for the light intensity to decrease to 0 should be as close to 10 minutes as possible. The time must not be less than 10 minutes. It should be close to 10 minutes, but not 9.9 minutes. It's okay to be a bit more than 10 minutes, but not less than 10 minutes, but around 10 minutes. Understand? Around 10 minutes, but not less than 10 minutes. But it's okay to be a bit more than 10 minutes, but around 10 minutes. You understood the question?
What about 10?
Fine. The time taken for the light intensity to decrease to 0 should be as close to 10 minutes as possible. As close to 10 minutes as possible. The time must not be less than 10 minutes. 9.99 minutes is not okay. But 10.1 minutes is okay. Understand? Fine. The diagram shows the student's design. Listen. The student uses a light emitting diode and a resistor R. The LED stops emitting light when the potential difference across it falls to 1.4 volts. The student assumes the LED has a constant resistance of 340 ohms. LED has a constant resistance of 340 ohms. And when the potential difference across the LED falls to 1.4 volts, LED will stop working. Capacitors with the following capacitances are available. They have given a few options. Determine which capacitance the student should use. The resistance of the fixed resistor is 860 ohms. Okay. Now, the question is which one will work? Who did this question? Who got the answer for this? What was your answer? 0. You mean 0.50, is it? What about the others? 0.56. 0.56. Okay, fine. Now guys, it's like this. When you put the switch to this position, the capacitor is now fully charged. The capacitor has a voltage of 12 volts. Okay. That 12 volts will be initially splitted across the fixed resistor and the LED. So the LED, the light, you know what is an LED, right? Light emitting diode. So when the current is passing through that, in the right direction, there will be a it will be emitting a light. Here they have given the specification of the LED. That means it needs a minimum of 1.4 volts to give a light out. When the question says the LED stops emitting light when the potential difference across it falls to 1.4 volts. Listen. So guys, when the LED's voltage stops to comes to 1.4 volts, that is the end of this circuit. I mean, the LED will stop emitting light. So we have to basically find a capacitor which will bring the voltage across the LED down to 1.4 volts in around 10 minutes. Understood? Exactly. Fine. So now we don't know the capacitance. I will take for the instance when the voltage across the LED has come down to 1.4 volts. For the LED, I will use V equals IR. V is 1.4. I into the R is 340. So that means at that moment, the current in the circuit is 1.4 over 340. 1.4 over 340 will be 7 over 1700. I will keep it as it for now. Amperes. Okay. Then for that moment, I will use it for the resistor R. The voltage is equal to IR. Voltage is 7 over 1700 into the resistance is 860. That is 3.54 volts. To be more accurate, 3.541 volts. That is the voltage across the resistor. So guys, the total voltage will be, which is the voltage across the resistor 3.541 plus the voltage across the LED, which is 1.4. Total voltage is 4.941. Okay. Agree. So now what I understand is initial voltage of the capacitor is 12 volts. And when that voltage reduces, and when it reduces to 4.941, the LED will stop emitting light. Am I right? I have checked the requirement for the LED to stop emitting light. The requirement for the LED to stop emitting light is the voltage across the LED has come down to 1.4. When the voltage across the LED has come down to 1.4, simultaneously the voltage across the resistor R has come down to 3.541. Agree? So which means the total voltage across the resistor and the LED is 4.941. That will be the voltage across the capacitor as well. Am I right? So which means when the voltage across the capacitor comes down to 4.941, the LED will stop emitting light. Do you understand that? .941 in a time of 10 minutes. Understood? So we know what? V equals V naught into e to the power minus t over RC. Then ln V equals ln V naught. We have this equation, right? Minus t over RC. Agree? So I'm going to use that equation here. T over RC equals ln V naught minus ln V. Okay. So T over T over RC. ln V naught minus ln V. ln V naught is 12 minus ln V is now 4.941. That I'm getting 0.887. Three. This is TORs. Okay. Right. So guys, T is T is equal to 0.8873 RC. Okay, listen carefully. We know the R, right? What is the R? Huh? No, not 860. It's 860 plus 340. Both are connected in series. So the R is how much? 0.8873. The R is 860 plus 340. 1200, right? 1200 times C. So T is equal to 0.8873 into 1200, which is 1064.76 C. Okay. Now the T should be what? More than T should be greater than or equal to 600 seconds, right? Not less than 600. Agree? So I will check the options available. 10,064.76 multiplied by 0.5. That gives me 532. No, the first one is rejected. Then 0.51. That gives me 543. That is also rejected. 0.54. That gives me 574. Rejected. 0.58. That gives me 617. So I will go with 0.58 farads. Understood. Which capacitor will make, because I got T equals 1064.76 into C. So which C value will make the T greater than or equal to 600? So I found 0.58 is the fellow doing it. If you have any questions, you can ask. Yes, right, you're right, very good. Okay. Don't just copy it. Give yourself a minute and try to absorb it. Huh?
T equals 600.
Okay.
And the capacitances are what it is.
600, what is the critical value of the C? 0.56. So then, yeah, that's the way. If you use that one at this point, it can be a bit confusing for you all if I just use 600. The reason that without putting T equals 600 and finding the C, I just did a trial and error by substituting each C value to see which will make the T more than 600. Okay, because I didn't want to use too much maths here. If you are comfortable with that, there is one thing I can do, but some people might be confused with this. Look at this.
So then this will use initial current.
Give me a minute, guys. I got T equals 1064.76 C, right? Okay. If you have a good math background, you will understand this. Look at this. So guys, I want the T to be greater than or equal to 600, right? So which means 1064.76 C is the T that should be equal to greater than or equal to 600, right? So which means the C should be greater than or equal to 600 divided by 1064.76, right? So that means C should be greater than or equal to 600 divided by 1064.76, which means it should be greater than 0.563. So out of the options available, the one which is greater than 0.563 is 0.58. That way, without a trial and error, you can derive at the answer. You can arrive at the answer. But I didn't want to do it because some people might think that is too much maths. Okay, so if you are comfortable with this, definitely you can do this and straight away arrive at the answer. Otherwise, you can just do a small trial and error and see which C value will give the correct time. No, definitely no, only for 0.58. Because I am getting C is greater than or equal to 0.563. So if you use 0.56, then that means the time will be less than 10. Why should they give marks for 0.56?
0.6.
No. 0.6 you are telling. No. If you have read the question clearly, the question says, okay, the student uses a light emitting diode and a resistor R. The LED stops emitting light when the potential difference across it falls to 1.4 volts. The students assume the LED has a constant resistance 340 ohms. Okay. And also here they have told, look at this. If you read this statement, the time taken for the light intensity to decrease to 0 should be as close to 10 minutes as possible. Okay. If you read that statement, it should be as close to 10 minutes as possible. Then you can't take 0.6, because when you take 0.6 farads, the time that is going to be taken will be more than the time when you use 0.58. You get my point? So when you have the option of 0.58, you can't use 0.6 to meet the given requirement. Then fine, because they have told it should be as close to 10 minutes as possible. Understood? So the only answer is 0.58. I think I already answered your question, Farviz Fazlul. Can we use 0.6 farad? No. It should be greater than 0.563. At the same time, you have to pick the first option available. More than 0.563, the first option available is 0.5. Understood. Right, what's next? Oh, there's another part in there. In part B, in practice, the resistance of the LED in practice, the resistance of the LED does not stay constant. The graph shows how the current varies with potential difference for the LED. Now, we did the previous calculation based on the assumption that the LED's resistance remains constant. Okay. But the question says in practice, the resistance of the LED does not stay constant. The graph shows how the current varies with potential difference for LED. Current versus voltage graph is given. Explain how the behavior of this LED shown in the graph will affect the time taken for the light intensity to decrease to 0. What do you think? If the LED's current versus graph is going to be this, how this is going to affect the time taken for the LED to shut down? Will it be more or less, or will it be the same? What do you think?
Be more. It will be more, sir.
It will be more. Why?
Because current is increasing, right? So if current increases, that means there's less resistance.
Okay, guys, now listen. So according to this potential current versus PD graph, listen to me. As the PD is increasing, when the PD is increasing, what is happening to the resistance of the LED? Is it increasing or decreasing? When the PD is increasing, the resistance is decreasing. Do you understand that? Am I right? When the PD is increasing, the resistance is decreasing. Okay. No. Okay, let me explain it for those who need it. I will just take a random point here. At this point, I over V resistance is given by I over V. Sorry, resistance is given by V over I. I over V is this much, this slope. At this point, that I over V, the slope is high here. So when the voltage is increasing, the I over V ratio is increasing. When the voltage is increasing, I over V ratio is increasing. I over V ratio is increasing means V over I ratio will be decreasing. Which means R is not equal to V over I, right? So which means when the voltage is increasing, the resistance is decreasing. This is what you have learned for AS levels and indeed O levels. How to look at an IV graph and decide what is happening to the resistance. Okay. So gradient, the I over V
Sorry,
ratio.
sir, time will be decreasing.
Oh, wait. Patience. I over V ratio is increasing as the voltage increasing. So the resistance is decreasing. Now listen to me. So guys, now when you switch on this circuit, the voltage across the LED is decreasing with time. Am I right? Voltage across the LED is decreasing. So voltage across the LED is decreasing means the resistance of the LED will increase with time. Am I right? According to this graph, I understood when the voltage increases, the resistance will decrease. So which means when the voltage is decreasing, the resistance should increase for an LED. In the given circuit, when the time is increasing, the voltage across the LED is decreasing. Am I right? Yes or no? So with time, as the time increases, voltage across the LED is decreasing, which means the resistance of the LED is increasing. The resistance of the LED is increasing means the overall resistance is increasing. There is something called this T equals RC, the time constant, you remember. So if the resistance is increasing, this time constant is going to increase. Okay. So when the time constant is increasing means, that means the voltage of the capacitor to reduce will take longer. So which means the voltage across the LED to come down to 1.4 volts will take longer. So that means earlier the LED went off in 10 minutes. Now it will take definitely longer than 10 minutes. Understood. What is your question?
Question is, show the voltage increases and the resistance. Graph is different.
Why? The graph shows when the voltage is increasing, the resistance is decreasing. Do you agree with me? When the voltage is increasing, resistance will decrease. So that means it's the same thing now I'm telling you. When the voltage is then decreasing, the resistance will increase. Where? The current versus potential. Current is increasing as the potential is increasing. So, how are you connecting the voltage here? No, tell me what is your question? Okay, I repeat. According to the graph, as the voltage increases, the resistance will decrease. Okay, so which means the same thing I'm telling other way around. That means when the voltage is decreasing, the resistance will increase. Okay, same thing.
So there is a lower capacity.
To get this done, yes. If you want to have the cutoff time at 10 minutes, now we can go for a lower capacitor, but that is not what they're asking. Okay, right. So when the voltage is decreasing, the resistance will increase. So when you keep this circuit on for some time, with time, what is going to happen? The voltage across this LED is going to decrease, right? Voltage across the LED is decreasing means voltage across the LED is decreasing means its resistance is increasing. Okay. Its resistance is increasing means the time constant RC product is increasing. So what we learn by time constant, if you can remember, it is the time taken for the voltage to reduce by a certain percentage. Like we found that percentage value as well, if you can remember, a few weeks back. What is the percentage? 37% or something. It is the time taken for the voltage to come down to 37% or something, some value. So anyway, you don't need to know that value. The time constant is increasing means the voltage, the time taken for the voltage to reduce across the capacitor will increase. So which means now for the voltage across the LED to come down to 1.4 volts will be more than the earlier time. Understood? That will get you the 3 marks definitely, right? The answer. As the voltage decreases, as the voltage across the LED decreases, as the voltage across the LED decreases, its resistance will increase. Its resistance will increase. Full stop. So the time constant will increase. So the time constant will increase. And the time taken for the LED to reduce its voltage to 1.4 volts will be higher. Okay. Is that okay? Right. The next one. The student states a capacitor is being used in this circuit. The function of the capacitor is to store electric charge. Explain why this is not a complete description of the function of a capacitor. Guys, just merely stating that a capacitor is being used to store charge is actually wrong. The reason, if you take a capacitor, it has two plates. One plate will store a positive charge. The other plate will store an equal amount of negative charge. Okay. So if you take the overall charge in the capacitor, it's 0. Okay. So actually, the capacitor doesn't store charge. It stores what? Electrical energy. Okay. The capacitor separates the charge. So that electrical energy is what's stored in the capacitor, not the charge. Write the answer on the back.
Potential capacity maintains the voltage in the circuit.
Here and here. The key point is you have to mention that overall charge is 0 and it stores electrical energy, right? A capacitor has two plates. A capacitor has two plates. Full stop. One stores a positive charge. One stores a positive charge. And the other stores an equal amount of negative charge. One stores a positive charge and the other stores an equal amount of negative charge. Full stop. So the total charge stored is 0. So the total charge stored is 0. A capacitor separates the charge. A capacitor separates the charge. So it stores electrical energy. So it stores electrical energy. What's next? 27. The photograph shows a demonstration AC generator used in a school. The handle is used to rotate the coil. The handle is used to rotate the coil between the magnetic poles. There's a north pole and a south pole. When a light emitting diode, LED, is connected across the coil, the LED flashes on and off as the coil rotates. Explain this observation. Guys, what do you know about an LED? It emits light. This is a circuit symbol of an LED. It emits light when? Huh? When does the LED emit light?
So when current passes through one direction?
Correct. A diode will function only when the current is passing through it in one direction. You know that, right? So guys, when the current is passing through this LED in this direction, yes, there will be a current passing through the LED. So there, the LED will emit light. But if the current is trying to pass through this direction, trying to pass through that direction, the current will not be able to pass through it. So LED will not emit light. Okay. Right. Knowing that, how is that relevant here? The handle is used to rotate the coil between the magnetic poles. When a light emitting diode is connected across the coil, the LED flash on and off as the coil rotates. Explain this observation. So there is you're rotating the handle, turning the handle. The coil is rotating, and there's a north pole and a south pole. So guys, when the coil is turning, it cuts the magnetic field between the north pole and the south pole. There will be an EMF induced, and that EMF induced will be an alternating EMF induced. Okay, when it keeps turning. So the current which is passing through the LED will be an alternating current. So the current which is passing through the LED will be an alternating current. Okay, but LED will function only when the current passing through it in one direction. Let's say it allows the current to pass through this direction. Then in this direction, the current will be zero through LED. Again, the next half of the period, there will be a current. Okay, so LED will allow the current pass through it only in one direction. So half of the time period, there will be a current. The other half of the time period, no current. Again, the next half of the period, there's current. The following half of the period, there's no current. So the current passing through the LED will be on, off, on, off, on, off. So which means the LED will be flashing. Am I right? Is that clear? So right. When the coil is rotating, it's raining. When the coil is rotating, it will cut the magnetic field lines. And there will be an EMF induced in the coil. There will be an EMF induced in the coil. Full stop. This will be an alternating EMF or alternating voltage. This will be an alternating voltage. Full stop. LED will allow the current pass through it. LED will allow the current pass through it only in one direction. LED will allow the current pass through it only in one direction. Full stop. So the current through the LED will on and off alternatively. So the current through the LED will on and off alternatively. I think that should be enough for 4 marker. Or maybe the last statement you can say, so the LED flashes on and off. The next one, part B. The output
Sir,
potential.
can you go back, sir, for 1 minute, sir, please? Thank you, sir.
Okay,
magnetic flux linkage changes, there is a
correct. When the magnetic flux linkage changes, not when there is a magnetic flux linkage. Okay, right. The output potential difference for the generator is recorded using a data logger, and a graph is produced of V against time. Add to the graph to show the output if angular velocity of the generator coil is halved. Guys, now if the generator coil is rotated at half the speed, how will be the graph? So wait, don't draw this. Tell me if this is correct. Angular speed is half, right? What if I draw something like this? Is this correct? Is this correct? Hello? The angular velocity is half. You're rotating the coil at half the speed now. So that means the time taken to complete a cycle will be half. Is this correct? What's wrong with it? What?
the velocity is half, time will be double.
Time will be double. So then what if I draw something like this then? Look at this. Okay, look at this, guys. What if I draw something like this? Is this correct? Why? The time period is double now.
The voltage should be half and use EMF.
What's wrong with this? Tell it again. Very good. So guys, now you're moving in slowly means the magnetic flux linkage will be cut at half the rate. No? Yes, moving in slowly means the rate of change of magnetic flux link will also reduce. So that means EMF induced will also become half. So what about this one then? Something like this. What do you think about this? Should be fine, no? Amplitude becomes half. The time period will double. So it has to be a graph like this. Those who haven't done it, take it down. Use a pencil, no? No. This color of pencil is a bit hard. Because they have told the speed is half and the velocity is half. Angular velocity is the amount of feedback that happens. How do you half complete? Somewhere here. Use a pencil. Whenever you use pen for a graph, if you do that and make a mistake, don't. Right, here's the next part. Explain the changes in the graph when the angular velocity of the coil is half. Huh? The same thing they're asking, right? Explain the changes in the graph when the angular velocity of the coil is half. Okay, so you have to write it in words, right? Explain the changes. Since the angular velocity is half, the time period will be doubled. Since the angular velocity is half, the time period will be doubled. Okay, full stop. Since the rate of change of flux linkage is halved, since the rate of change of flux linkage, since the rate of change of flux linkage is halved, is he going to draw you at the exam as well? Since the rate of change of flux linkage is halved, the amplitude will be half. You're asking about the graph? Amplitude will be halved. Amplitude of the graph will be halved. Is that okay? Right, guys, the next part, part 3. The coil rotates in a uniform magnetic field at an angular velocity. The average magnitude of V is 3.2 volts. Determine the number of turns in the coil. Magnetic flux density is given, the cross-sectional area is given. Right. At the original angular velocity. What is the original angular velocity? Have they given the value? No, but we know the time period, right? What is the time period? .2 seconds, no? Time taken is 0.2 seconds. From the graph. 0.2, no? The time taken for one complete circle.
So that's half a circle, eh? Okay, with when it's not half.
The question says the coil rotates in a uniform magnetic field. We don't know which field they are talking about here, not the previous field. At the original angular velocity. So the original angular velocity is the graph what they have given here. This is what given originally. No. They are telling the coil rotates in a uniform magnetic field, not the previous magnetic field. It's a separate uniform magnetic field. at the original angular velocity. The angular velocity what they have given. For the angular velocity what they have given, the time period is 0.2 seconds. Correct? So magnetic, the time taken for one turn is 0.2 seconds. Now the coil rotates in a uniform magnetic field at the original angular velocity. The average magnitude of V is 3.2 volts. Magnetic flux density is 0.083 Tesla. So guys, the magnetic flux will be, if I take it as phi, that will be B into A, 0.083 into 0.0048. That is 3.984 into 10 to the power minus 4. This is the magnetic flux. Okay. So the magnetic flux linkage will be, this phi multiplied by the number of turns, right? Which is 3.984 into 10 to the power minus 4 into 8. So the EMF induced is rate of change of magnetic flux linkage, which is 3.984 into 10 to the power minus 4 into n, divided by the time taken, 0.2 seconds. That is equal to 3.2. From here, you can find the number of turns. $1,606, no? Yeah, so we'll take it as 1,600 or 1,610 for 2 or 3 significant figures. Here, 1,606 is also fine. You can just leave it. At least if you have 2 or 3 significant figures, enough. We'll take a small break, no? See you in 15 minutes. Hi. Okay, guys, what's next? Uh, 28th one is we can't do it still. Just skip that question. 26, 8. 29th one. Sorry. Yeah, 29th. The photograph shows a model electric motor. A coil of wire is mounted between two magnets. When there is a current in the coil, it rotates. The diagram shows the position of the coil viewed from one end. When it is at an angle of 20 degrees to the horizontal. The current is into the page at X. The current is into the page at X. And out of the page at Y. Okay. Now listen carefully. There are 10 turns on the coil, and the current in the coil is 6.9 amperes. Determine the resultant moment about P of the magnetic forces acting on the coil. Length of the coil is given, width of the coil is given, current in the coil is given, number of turns is given, magnetic flux density is given. Okay. 28th we can't do still actually. Guys, anyone who got the answer for this? What is your answer? Okay, let's see. Now, do you understand this diagram? It's a coil, a rectangular coil. What you see here is just one of the four sides of the coil. Okay. Exactly. From this point X, the current is going into the plate, and then it goes like this. And from point Y, it is coming out of the plate. Agree? It is, give me that tube, please. The coil is at an angle. Okay. What is given is the point X and Y. The point X is this vertex. Point Y is this vertex. Correct? From the point X, the current is going in, and then it goes in a cycle. And from this point Y, it comes out. So the current is going from Y to X, and this is the cycle. It is a rectangular coil, and there are 10 coils like that. It says 10 turns on the coil. Do you understand the diagram? Okay. Now they are asking you for the turning effect, the resultant moment about point P. Resultant moment about point P. Listen. So guys, if I use Fleming's left hand rule for the wire which is passing through X, the magnetic field is this way. Field is this way. If I use Fleming's left hand rule, current is into the page. So the force on this will be downwards. For the wire which is connected to the point X, the force is downwards. Okay. The force on this piece of wire will be upwards. Agree? So this is going to cause an anticlockwise movement. Is that okay? Right? So to see what is that force, if I use F equals BIL, F equals magnetic flux density is 0.07, current is 6.9, into the length of the coil is given 5 centimeters, which is 0.05. That will give you the force acting on one piece of wire. That is 0.024 15 Newton. Okay. So there are 10 number of turns 10. There are 10 of those. So if I take the F total to be F into 10, which is 0.2415 Newton. Agree? And also, guys, there is a force on each side. And we know that this length is given, this width is given how much? 3.5 centimeters. This is given 3.5 centimeters. Okay. Since that is 3.5 centimeters, from P to I, this length will be half of 3.5 centimeters, which is 1.75 centimeters. Half of 3.5, 1.75 centimeters. But I want the perpendicular distance from here to here. This perpendicular distance is what I want. So if I put up a small triangle here, this is 20 degrees. This is 1.75. This is if I take it as D. D equals 1.75 cos 20. 1.75 cos 20 will be 0.714. Don't forget that it's in centimeters. Okay. So here is my final answer. The moment caused by one of these two forces will be 0.2415 multiplied by 0.714 divided by 100 to convert centimeters to meters. That is the moment causing by one of the two forces. There are two forces like that. I'll multiply that by 2. Correct? This force is causing an anticlockwise movement, and this is also causing an equal amount of anticlockwise movement. So I have multiplied that by 2. Which I'm getting 3.45. Into 10 to the power minus 3 in Newton meters. Is that okay? Bit louder. About 0.3. Okay. Yeah, one of the forces into the distance between, because it's a force topic. If you are taking this total distance, then you don't have to multiply by this distance. So that's why I multiply by 2.
So can you explain how it is supposed to be done?
Fleming's left hand rule.
It's not working.
Why it's not working?
I don't know.
Here the current is into the wave.
Yeah.
If B is this way.
How is it correct?
You read the question.
Yeah.
From the point X it is into the page. From the point 5 it is out of the page. Current is going like this. Okay. So at point X there is a wire into the paper. Current going in. So I is in, B is this way. Force is down.
Okay.
Right? The 30th one. Right, guys, turn to question number 11. Question number 11. We will start with the next topic, the next class, okay? Today we won't be able to start it. Turn to question number 11. So we'll start nuclear and particle physics next class. You guys read question 11. Question 11, read the question. That is not states about the magnitude of superheaps is connected to what? Yeah, next week there will be no class. Right, there's a student uses, listen guys, a student uses a strong cylindrical magnet to investigate Lenz's law. The student records the time taken for the magnet to fall through 2 hollow tubes of copper. The student records the time taken for the magnet to fall through 2 hollow tubes of copper, tube A and tube B. The 2 tubes have the same length, cross-sectional area. B has a vertical slit cut into it, as shown. Discuss the differences in the time taken for the magnet to fall through each tube. Okay, now stop your work and listen to me. I think we have answered a similar question last class. Listen. Guys, now if you take this magnet, okay, and forget about these 2 tubes, there's no 2 tubes. You just let it drop. Okay, you just let it drop, and there's no air resistance or anything. It will fall under gravity, right? It will fall with an acceleration of 9.8. It will fall under gravity. Okay. Now, if you take this magnet and make it fall through this copper tube, okay, if it is falling through copper tube, for it to reach the ground, will it take a longer time or a lesser time compared to earlier? It will take a longer time. Why is that? There will be a resistive force acting on the magnet. Correct? The reason? Okay, now wait, now we have to explain this for 6 marker. Why will be the time taken be higher? because when the magnet is moving, magnetic field lines are cut by the copper. So there will be an EMF induced. Yeah, magnetic flux linkage changes. So there will be an EMF induced in the copper wire. So that means there will be current in the copper wire. So that current in the copper wire will be in such a way to oppose the change causing it. So which will result in an upward force on the magnet by the copper wire, by the copper tube. So due to that upward force, the magnet will take relatively a longer time. Agree? Fine. Now that same magnet, we make it pass through another copper tube, which is identical to the tube A. But the only difference is, here there's a slit. There's a cut in the tube. Now tell me, if the time taken for the magnet to fall through this is TA, and if the time taken for the magnet to fall through this is TB, which will be greater? TA is greater. Is it? Reason? That's it. Huh?
The field excited on the magnet by the copper will be less.
In B, it will be less. Why? Yeah, guys, because of this slit, there is less path for the current in this one. There is less path for the current in this one. So in this case, the induced current will be less.
So that
Here this is complete, no. Since it's a whole tube, current has more path and there will be more current developed. Okay, so because there's more current developed, here the opposing force will be more. Here the opposing force will be relatively less. Okay, so in the case B, the opposing force is less, so the time taken will be lesser compared to the one in A.
so that the current flow will be present with the R3 is complete.
Yeah.
Due to the state, there won't be a current.
There will be current. It doesn't have to be this way. No. It can be a current flowing from here to here also. It can be a current flowing from here to here also. You actually call that eddy currents. What currents? Eddy currents. Due to the difference in the voltage at different points, there will be so many different chutu currents inside them. You call that eddy current. You don't have to use the word eddy. Right? Fine. Right? Volume. No, then you can't make a comparison actually, because then it's not identical tubes. There will be other factors which will be affecting it. You can't be tested on those questions, right? As the magnet falls, as the magnet falls, the magnetic field lines are cut by the copper tubes. And there will be an EMF induced in the tubes. As the magnet falls, the magnetic field lines are cut by the copper tubes, and there will be an EMF induced in the tubes. Full stop. So there will be a current in the tubes, and it will be in such a way to exert an upward force on the magnet So there will be a current in the tubes, and it will be in such a way to exert an upward force on the magnet as per Lenz's law. Full stop. The force exerted by tube A will be higher. Force exerted by tube A will be higher than the tube B, since A has more paths for the currents to flow. Full stop. So the time taken for the magnet in A will be higher than in B. Should be fine. Read the answer and see. If you have a question, you can ask me. So guys, there can be just one or more two questions remaining in this tube. I'll leave it to you. Please complete it. So the next day we are starting with particle and nuclear physics. Students online, I have mailed the tube. And if you want to get it physically, you can come and collect it from your place. Okay. Bye. See you. Take care. Have a nice weekend. See you. Next week there's no class. So we will be meeting week after next. Bye. See you. Take care.
Bye, sir. Thank you.
Bye. See you. Yeah, I think after coming here, I think you have sent me, but I haven't checked it. So please send me a reminder again. I will check it.